The lattice energy of a crystalline solid is usually defined as the energy of formation of the crystal from infinitely separated ions and as such is invariably negative. The concept of lattice energy was originally developed for rock-salt-structured and sphalerite-structured compounds like NaCl and ZnS, where the ions occupy high-symmetry crystal lattice sites. In the case of NaCl, the lattice energy is the energy released by the reaction Na plus Cl minus NaCl, which would amount to minus 786 kilojoules per mole. Some older textbooks define lattice energy with the opposite sign, i.e., the energy required to convert the crystal into infinitely separated gaseous ions in vacuum, an endothermic process. Following this convention, the lattice energy of NaCl would be plus 786 kilojoules per mole. The lattice energy for ionic crystals such as sodium chloride, metals such as iron, or covalently linked materials such as diamond is considerably greater in magnitude than for solids such as sugar or iodine, whose neutral molecules interact only by weaker dipole-dipole or van der Waals forces. The precise value of the lattice energy may not be determined experimentally, because of the impossibility of preparing an adequate amount of gaseous ions or atoms and measuring the energy released during their condensation to form the solid. However, the value of the lattice energy may either be derived theoretically from electrostatics or from a thermodynamic cycling reaction, the Bourne-Haber cycle. The relationship between the molar lattice energy and the molar lattice enthalpy is given by the following equation, where is the molar lattice energy, the molar lattice enthalpy and the change of the volume per mole. Therefore the lattice enthalpy further takes into account that work has to be performed against an outer pressure. Theoretical treatments. Bourne-Landé equation. In 1918, Bourne and Landé proposed that the lattice energy could be derived from the electric potential of the ionic lattice and a repulsive potential energy term, where Na is the Avogadro constant, M is the Madelung constant. Relating to the geometry of the crystal, Z plus is the charge number of cation, Z minus is the charge number of anion, QE is the elementary charge, equal to 1.60220000000001.6022 times 10⁻19 C. Epsilon 0 is the permittivity of free space, equal to 69888854000000008.854 times 10⁻12 C2J-1 meter-1. R0 is the distance to closest ion, and n is the Bourne exponent, a number between 5 and 12, determined experimentally by measuring the compressibility of the solid, or derived theoretically. The Bourne-Landé equation gives a reasonable fit to the lattice energy. From the Bourne-Landé equation it can be seen that the lattice energy of a compound is dependent on a number of factors. As the charges on the ions increase, the lattice energy increases. When ions are closer together, the lattice energy increases. Barium oxide, for instance, which has the NaCl structure and therefore the same Madelung constant, has a bond radius of 275 picometers and a lattice energy of minus 3054 kilojoules per mole, while sodium chloride has a bond radius of 283 picometers and a lattice energy of minus 786 kilojoules per mole. Kapuscinski equation. The Kapuscinski equation can be used as a simpler way of deriving lattice energies where high precision is not required. Effect of polarization for ionic compounds with ions occupying lattice sites with crystallographic point groups C1, C1H, Cn or Cnv. The concept of the lattice energy in the Bourne-Haber cycle has to be extended. In these cases, the polarization energy EPOL associated with ions on polar lattice sites has to be included in the Bourne-Haber cycle, and the solid formation reaction has to start from the already polarized species. As an example, one may consider the case of iron pyrite Phase2, where sulfur ions occupy lattice site of point symmetry group C3. The lattice energy defining reaction then reads Fe2++ 2 pol S- Phase2, where pol S- stands for the polarized, gaseous sulfur ion. It has been shown that the neglection of the effects led to 15% difference between theoretical and experimental thermodynamic cycle energy of Phase2, that reduced to only 2% when the sulfur polarization effects were included.